Your PCB design can be perfect. Your schematic can be clean. Your routing can follow every single rule in your book, and your board still fails. The reason is not something you can easily see inside your ECAD software. It's what happens when your digital signals start interacting on the physical board. This is PCB signal integrity, and most engineers only truly understand it after the failure. In low-speed circuits, wires are just wires. They are simple copper connections. But in high-speed PCB design, they stop behaving like wires. They transform into transmission lines. And once that happens, everything changes. Signals start to reflect back to the source, noise couples onto adjacent traces, return paths break completely, and timing margins shift out of spec. And the worst part? You cannot always see this in your schematic or layout preview. It looks flawless on your monitor, but it's a mess in physical reality. Signal integrity simply means how cleanly a signal travels from point A to point B without distorting. But in real PCB design, it is never about the signal trace alone. It is entirely about the environment around that signal. We are talking about your layer stackup, the proximity of your ground planes, the physics of your VAs, your overall trace geometry, and the path the return current takes. So, remember this. Signal integrity is actually system behavior, not just individual trace quality. This is where most engineers get it wrong. They hyper-focus on the signal trace itself, but they completely ignore the return path. When a high-frequency signal travels down a copper trace, it always needs an equal and opposite return current path directly underneath it. If that path is broken by a split plane or forced to take a long detour around a slot, your impedance spikes, noise couples into surrounding circuitry, EMI radiates like crazy, and your timing becomes completely unstable. This broken return path is one of the most invisible, devastating failure points in hardware engineering. Your PCB stackup defines everything before you even place a single track. It dictates your controlled impedance, governs the electromagnetic coupling between your layers, and determines your reference plane quality. If your high-speed signal layer does not have a solid, continuous reference plane directly underneath it, your signal is basically flying blind through the dielectric. And this is why your stackup is never an afterthought. It is the foundational design decision you must make before routing ever starts. Let's look at what actually causes these failures in production. Take a broken ground plane under a high-speed trace. It forces a massive return path detour, creating a loop antenna that distorts your signal. Or look at parallel traces packed too close together. The energy bleeds over, causing crosstalk and crippling data corruption. Even a simple via transition without planning creates an immediate impedance mismatch, sending signal reflections bouncing back down the line. These are not rare edge case scenarios. These are daily PCB design disasters. Instead of looking at your screen and thinking, is my trace correct? You should constantly be asking, what physical path is my return current taking right now? And what happens to the electromagnetic field when this signal switches layers through a VIA? Because ultimate signal integrity is not about routing pretty lines. It is about controlling the physics of electricity on a physical board. Here are 3 rules that will immediately improve your designs and save your next spin. First, never break a reference plane under high-speed traces. Second, always simulate and design your stackup before you touch a single route. And third, treat every single high-speed trace as a transmission line, not a wire. These 3 rules alone will eliminate the vast majority of your signal integrity issues. Now I want to know something from you. Have you ever had a PCB that looked absolutely perfect in your software, but completely failed on the test bench? Tell me what went wrong in the comments below. And if you want more real-world PCB breakdowns, not textbook theory, but actual engineering behavior, subscribe.